Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The landscape of theoretical physics in the mid-20th century was shaped by a profound and triumphant unease. The development of quantum electrodynamics and its subsequent renormalization program provided a calculational framework of unprecedented accuracy, yet for a select group of its deepest thinkers, including Paul Dirac and Hideki Yukawa, this success felt philosophically hollow. The procedure of subtracting infinite quantities to arrive at finite predictions, while pragmatically powerful, seemed an admission of a fundamental flaw in the conceptual bedrock of the theory, namely the assumption of point-like elementary particles and their local interactions. It is against this backdrop of intellectual dissatisfaction that one must situate Yukawa's 1954 treatise, Quantum Theory of Non-Local Fields Parti-Free Fields. This work represents a radical and elegant attempt to rebuild quantum field theory from a new foundation, proposing that the elementary constituents of reality possess an inherent spatial extension. This essay will undertake a direct and systematic evaluation of the internal claims, mechanisms, and logical structure of Yukawa's paper, proceeding section by section to analyze the specific arguments he marshals in constructing the kinematics of a free, non-local quantum field. We will explore the architecture of his proposal, through the introduction of the bilocal field to the derivation of a mass spectrum, assessing the coherence and implications of each conceptual step within the self-contained universe of the paper itself. Section 1. The foundational postulate of non-locality. Yukawa commences his argument by directly confronting the idealization of the point particle. His core claim in the introductory passages is that the divergences plaguing quantum field theory are an unavoidable consequence of this geometric simplification. He posits that a more physically realistic model requires a departure from locality, introducing a new description for elementary particles that incorporates an internal structure. The evaluation of this initial claim rests upon its motivation and its consequences. Yukawa's argument is one of physical intuition, suggesting that the concept of a mathematical point is an abstraction that breaks down at the scales where quantum effects and particle creation are dominant. He proposes to replace the field variable dependent on a single spacetime point, typically written as phi of the spacetime coordinate x, with a more complex object dependent on two spacetime points. This object, which he would soon formalize as a bilocal field, inherently contains a notion of extension. The central assertion evaluated here is that such an extension can serve as a natural physical regulator, effectively smearing the singular interactions that produce infinities. The methodology is one of bold conjecture, a refounding of principles. The evidence he presents is circumstantial, resting on the failures of the existing local theory. He is essentially claiming that since the local theory leads to infinities, the locality principle itself is the flawed axiom. This is a powerful and intellectually clean argument, and within the paper's own logic, it serves as a compelling justification for the complex mathematical apparatus that is to follow. He is asking the reader to accept, as a primary postulate, that elementary particles are fundamentally extended objects, a claim whose validity the rest of the paper seeks to demonstrate through the construction of a consistent theoretical frame. Section 2. The formalism of the bilocal field. Having established his motivation, Yukawa proceeds to the formal definition of his central object, the bilocal field. This section claims that a quantum field can be consistently described by a function u of two spacetime 4 vectors, which we can call x prime and x double prime. He immediately simplifies this by a change of variables, representing the field as u of capital X and small r, where capital X represents the center of mass coordinate, defined as 1/2 of the sum of x prime and x double prime, and small r represents the relative displacement vector, x prime minus x double prime. The evaluation of this claim focuses on its structural implications. This formulation is an elegant mathematical maneuver. The capital X coordinate is intended to describe the motion of the particle as a whole through spacetime, while the small r vector describes the internal structure and extension of the particle. The claim is that the laws of physics can be separated into these two domains: an external, center of mass motion, and an internal, relative motion. This separation is the key mechanism that allows the theory to retain familiar concepts like momentum and position for the particle as a whole, while introducing entirely new physics associated with the internal degrees of freedom. Critically, Yukawa posits that this bilocal field is an irreducible entity. It is not a composite of two more fundamental point-like fields. The internal vector r is as fundamental to the particle's description as its external position x. Assessing this framework reveals its immense ambition. By encoding extension into the fundamental field object, Yukawa is proposing a new kind of elementary particle, one with internal dynamics. The specific claim that this center of mass and relative coordinate system is a sufficient and consistent basis for a new kinematics is the central pillar of this section. Its success depends entirely on whether physically sensible equations of motion and quantization conditions can be constructed upon it, a task he turns to near. Section 3. The equations of motion for the free field. This portion of the paper advances the crucial claim that the dynamics of the free bilocal field can be governed by a set of two simultaneous differential equations. Yukawa proposes a specific form for these equations, asserting their consistency and physical relevance. The first equation governs the external motion, tied to the center of mass coordinate capital X. It takes the form of the familiar Klein-Gordon equation. Spelled out, this equation states that the Directives operator with respect to the capital X coordinates, which is the second partial derivative with respect to time minus the sum of the second partial derivatives with respect to the three spatial coordinates, acting on the field U, is proportional to a mass-squared term acting on U. The second equation, however, is novel and governs the internal dynamics associated with the relative coordinate r. Yukawa proposes an equation for this internal motion that is akin to that of a four-dimensional relativistic harmonic oscillator. It involves derivatives with respect to the components of the internal vector r. Specifically, he puts forth an equation stating that a combination of the Directives operator with respect to the internal coordinates and a function of the internal coordinates themselves, acting on the field u equals 0. The evaluation of these claims is multifaceted. By using the Klein-Gordon equation for the external variable, Yukawa ensures that on a large scale, the particle-like excitations of his field will behave in a way that is consistent with established relativistic quantum mechanics. The particle as a whole has a well-defined momentum and energy. The more radical claim is the assertion of the harmonic oscillator-like equation for the internal structure. This choice is a specific, potent hypothesis. He is claiming that the internal dynamics of an elementary particle are harmonic. The evidence for this specific choice within the paper is one of mathematical convenience and power. The harmonic oscillator is one of the few exactly solvable systems in quantum mechanics. Its solutions are well known to be discrete and quantized. By postulating this form, Yukawa is explicitly building a machine for generating discrete properties from the continuum of the internal coordinates. The logical coherence is sound if one accepts the bilocal premise: one needs equations of motion. This pair represents a plausible, solvable first attempt that bridges the familiar with the entirely. Section 4. The generation of a discrete mass spectrum flowing directly from the dynamics of the internal coordinates. Yukawa makes his most spectacular claim that a single bilocal field does not describe a single particle of a single mass, but an entire tower of particles with a discrete spectrum of masses. This section of the paper details the mechanism by which this mass spectrum emerges. The internal harmonic oscillator equation, upon quantization, yields discrete energy eigenvalues. From the perspective of an observer concerned only with the external, four-dimensional spacetime of the coordinate capital X, These discrete internal energy levels manifest as different contributions to the overall rest mass of the particle. The total mass squared of an excitation is given by ground state mass plus contributions from the quantized modes of the internal oscillator. The evaluation of this claim must appreciate its revolutionary nature. Yukawa is claiming to have found a dynamical origin for the existence of different elementary particles in the context of the 1950s. With new mesons being discovered in cosmic rays and accelerators, the idea that the seemingly arbitrary collection of particle masses could be the result of the excited state of a single, underlying non-local field was deeply profound. He is essentially claiming to replace the phenomenological list of particles in the Standard Model's precursor with a generative principle. The methodology here is a direct application of standard quantum mechanical techniques to a novel substrate. The logic is impeccable if the internal dynamics are governed by a quantized oscillator. Then a discrete energy spectrum is an unavoidable consequence. The profound implication, which Yukawa leaves somewhat implicit in this first paper on free fields, is that transitions between these internal states would correspond to decays of heavier particles into lighter ones. Here one can detect a flicker of intellectual wit in the sheer audacity of the proposal, an attempt to derive the very particle zoo itself from a single, elegant mathematical postulate about internal space. The claim's strength lies in its logical inevitability once the preceding assumptions are granted. Section 5 The quantization procedure and commutation relations, a classical field theory, however elegant, requires a consistent quantization procedure to make contact with quantum reality. This section of Yukawa's paper addresses this necessity, claiming that the bilocal field U of capital X and small r can be quantized by imposing specific commutation relations. This is perhaps the most technically challenging and conceptually fraught part of the entire non-local program. Yukawa proposes a generalization of the canonical commutation relations for a scalar field. For a standard local field, the commutator of the field phi at a point x and its conjugate momentum pi at a point y is proportional to a Dirac delta function centered on x minus y, enforcing microscopic causality. For the bilocal field, the situation is more complex. Yukawa formulates a commutation relation where the commutator of the field U at coordinates capital X and small r, and the field U dagger at coordinates capital X prime and small r prime, is given by a new mathematical object, a non-local delta function. This function depends on the separation of the center of mass coordinates and also on the internal coordinates r and r prime. The evaluation of this claim centers on its consistency and its physical consequences, particularly concerning causality. The introduction of a spatially extended object immediately raises questions about faster-than-light signaling. If a measurement at one end of the extended object could instantaneously affect the other end, causality would be violated. Yukawa's proposed commutation relation is carefully constructed to ensure that the commutator vanishes when the two center of mass points, capital X and capital X prime, are separated by a space-like interval, regardless of the internal coordinates. He claims that this is sufficient to preserve macroscopic causality. Signals cannot propagate faster than light between the centers of mass of two particles. The internal, space-like extension exists in a way that is causally disconnected from the external world. This is a subtle and powerful argument. He is attempting to build a theory that is non-local at the microscopic level of the particle structure, but remains causal at the macroscopic level of particle propagation and interaction. The claim is that his specific form of the commutation relations achieves this delicate balance. While later analysis, other physicists would continue to probe this issue, finding potential difficulties in interacting theories within the self-contained logic of this paper on free fields. Yukawa's construction is a coherent and ingenious attempt to quantize an extended object without immediately violating one of the most fundamental principles of relativity. Section 6 The propagator and the regularization of divergence is the final major claim of the paper, and the one that connects back to the original motivation is that this non-local formalism naturally produces a field propagator that is free of the singularities that plague local theories. The propagator, or Green's function, ascribes the amplitude for a particle to travel from one spacetime point to another. In conventional field theory, a propagator has a singularity when the spacetime interval between the 2 points approaches zero, which is the ultimate source of ultraviolet divergences in loop calculations. Yukawa demonstrates that the propagator for his bilocal field is different. By solving the Green's function for his coupled system of equations, he arrives at a new propagator. This mathematical object is effectively a smeared-out version of the standard Feynman propagator. The smearing is a direct consequence of the internal structure of the particle. The form factor arising from the internal wave functions acts as a convergence factor, a damping term that suppresses the contribution of very high momentum states and smooths out the singularity at the origin. The evaluation of this claim confirms that the mathematical machinery works as advertised. The internal harmonic oscillator wave functions, when integrated over, provide a natural cutoff. Yukawa is claiming to have solved the divergence problem, not by an ad hoc procedure of renormalization, but by building the regulator into the very fabric of the particle itself. The particle's finite size automatically prevents it from interacting at a single mathematical point, thus taming the infinities. This is the payoff for all the preceding conceptual and mathematical work. The claim is that non-locality, as he has formulated it, is a physical mechanism for regularization. This conclusion is logically sound within his framework. The resulting propagator is indeed regular. The paper successfully demonstrates that, at the level of the free field and its propagator, the non-local approach achieves its primary technical goal. The immense challenge, which this paper sets the stage for but does not broach, is whether this regulated propagator can be incorporated into a fully consistent, causal, and unitary interacting. In conclusion, Hideki Yukawa's 1954 paper on the quantum theory of free non-local fields stands as a monument of profound physical intuition and formal elegance. The evaluation of its internal claims reveals a work of remarkable logical coherence. From the foundational postulate that particles are extended, Yukawa systematically constructs a complete kinematic framework. His introduction of the bilocal field, governed by a dual set of equations for external and internal motion, is a powerful and direct implementation of this core idea. The subsequent claim that this framework naturally generates a discrete mass spectrum from a single field is a predictive masterstroke, offering a dynamical explanation for the proliferation of particles. Furthermore, his proposed quantization procedure, while raising subtle questions of causality, represents a sophisticated attempt to reconcile quantum mechanics with a non-local ontology. Ultimately, the paper successfully demonstrates its most central technical claim, that the formalism yields a regularized propagator, thus providing a physical, non-procedural solution to the problem of divergences that so troubled the architects of quantum field theory. While the non-local program would ultimately face formidable obstacles in the formulation of interactions and would be eclipsed by the continued triumphs of gauge theories and the renormalization group, this paper remains a vital document. It embodies a different path, a road deeply considered but less travelled, showcasing a compelling and self-consistent vision of a reality built not on infinitesimal points, but on fundamentally structured and extended entities. Its claims, assessed on their own terms, constitute a complete and powerful argument for a radical rethinking of the nature of elementary particles.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.